In a standard refrigeration cycle, refrigerant flows from the evaporator to the compressor, condenser, and expansion device. The compressor is the heart of this cycle, operating under a strict mechanical limitation. It is designed exclusively to process refrigerant in its vapor state. Internal pistons and valves actuate at high speeds, creating rapid pressure changes calibrated specifically for the density and compressibility of gases. While vapors are highly compressible, liquid refrigerants are essentially incompressible. When subjected to the extreme mechanical force of a moving piston, a liquid will not yield. Introducing an incompressible fluid into a high-speed vapor machine creates a fundamental physical mismatch. The resulting hydraulic stress leads to immediate mechanical destruction. When transient liquid refrigerant fails to evaporate and exits the cooling coil, the system enters a failure state known as floodback. This occurs when system variables fluctuate, specifically during periods of low evaporator load or when the expansion valve fails to maintain correct superheat parameters. Once liquid escapes the evaporator, it travels down the suction line as a dense mass, headed directly for the compressor intake. If this dense liquid strikes the fast-moving mechanical components of the compressor, the physical impact is completely catastrophic. This liquid slugging shatters internal valves, bends connecting rods, washes lubricant from the bearing assemblies, leading to total compressor failure. Because these thermodynamic errors are often inevitable during varying operation cycles, the system requires a structural intervention point before the intake. Engineers place the suction accumulator at this specific location on the low pressure line. This specialized fluid dynamic vessel is engineered to forcefully decouple the liquid phase from the vapor stream. To understand this separation, we have to look at the internal architecture of a vertical accumulator and how it manages different fluid densities. The low-pressure mixture of vapor, liquid, and oil enters the vessel directly from the evaporator suction line. As the mixture moves from the narrow pipe into the much wider internal chamber, its forward velocity drops instantly. This sudden reduction in momentum allows gravity to take over the phase separation process. The heavier liquid refrigerant and suspended oil lose their kinetic energy and fall to the bottom of the vessel. The lighter refrigerant vapor remains buoyant, continuing its path upward into the compressor intake tube. This decoupling occurs continuously, allowing the system to handle dynamic changes in refrigerant flow without interruption. By utilizing geometry to manipulate fluid velocity, the accumulator strips the dangerous liquid mass out of the flow path before it can reach the compressor. Separating the liquid creates a secondary problem. The compressor requires a constant supply of oil for lubrication and heat dissipation. Because this oil is heavy, it pools at the bottom of the accumulator alongside the trapped liquid refrigerant. This creates a paradox. The accumulator must trap the liquid to prevent slugging, but if it traps the oil, the compressor will seize from lack of lubrication. The solution is found in the specific geometry of the internal U-tube, which features a tiny aperture at its lowest point. This is the metering orifice. As refrigerant vapor rushes through the U-tube, it creates a pressure differential that draws fluid through this opening. A controlled micro amount of the liquid and oil mixture is siphoned into the vapor stream and pulled toward the exit. This fractional amount is small enough that the liquid refrigerant boils off safely, while the oil is carried back to the compressor crankcase. This engineered return system differs from a simple piping trap, which lacks the ability to precisely meter the volume of returning fluid. The calibrated size of the metering orifice ensures the compressor stays lubricated while maintaining a strict barrier against large-scale liquid slugging. While the physics of separation are constant, the physical shape of the accumulator often changes to meet the spatial constraints of the system. In low-profile mechanical chassis where vertical space is limited, engineers utilize horizontal accumulators. The same principles of gravity separation apply here, though the internal tubes and baffles are rearranged to ensure the liquid reservoir stays isolated from the suction intake. Some systems employ a heat exchanger accumulator combination for enhanced performance. This design uses heat from the high-pressure liquid line to actively boil off the trapped refrigerant inside the accumulator shell. Regardless of these external variations, the internal dimensions and orifice sizes are precisely set by the manufacturer to match the compressor's requirements. The spatial footprint may change, but the core objective of fluid deceleration and metered return remains the same. It is essential to distinguish the suction accumulator from the liquid receiver. The accumulator is located on the low-pressure suction side, where its primary job is to protect the compressor from liquid. The receiver is located on the high-pressure liquid side. It acts as a storage vessel to ensure a steady supply of liquid refrigerant to the expansion device. Their internal designs reflect these roles. The accumulator is built to separate vapor from liquid, while the receiver is built to provide a continuous column of liquid. In short, accumulators protect against unpredictable thermodynamic errors, while receivers manage the system's volumetric supply requirements. When an accumulator fails, the protection for the entire system is compromised. If the vessel is undersized, it can overflow during a severe floodback event, allowing liquid to enter the compressor unimpeded. If debris clogs the metering orifice, oil return stops. This leads to increased friction, heat, and eventual seizure of the compressor. Diagnosing these issues requires measuring the pressure drop across the vessel and comparing the temperature at the inlet and outlet. These temperature differentials indicate whether liquid is effectively pooling and boiling off, or if the vessel is becoming saturated. Simply replacing a failed accumulator is rarely the solution. The technician must address the root cause of the floodback at the evaporator or expansion valve. The suction accumulator serves as the primary defense in refrigeration, using fluid dynamics to stabilize the system against the instabilities of the thermodynamic cycle.